Okay, so we're gonna try something new today, but not new, entirely new. We're just gonna be taking something completely out of context and then somehow making some math out of it. So for today's lecture, what we're gonna be doing is we're gonna be taking pronouns out of context and we're gonna claim that pronouns are in fact quotient groups. Okay? So today, pronouns are quotient groups. So what exactly first of all, what exactly is quotient group? So you guys know about groups. Groups are structures, mathematical structures, such that it's a set that has a predefined operation over it, a binary operation that takes in two elements from the set and gives one element that's inside the set also, so that means it's closed. It's associative, so if I have three elements and then I do operation on two of them first and then do the third one and then I switch it around, it wouldn't matter. And it's associative, it has an inverse, so every element inside the set has another element such that if I do the operation on both of them, I get the identity element. And lastly, of course, the identity element is an element wherein if I apply it on any other element with respect to the operation, I get nothing. Essentially, I'm doing nothing to that other element. So if I have, like, for example, 1 is a multiplicative identity, 0 is an additive identity, because if I add 0 to any number, it just yields that other number. And if I multiply 1 by any number, it just yields that number. So those are examples of identities. So, alright, quotient groups. So this is a bit of an abstract topic to talk about, but the best way I can talk about it is via the modular arithmetic. Because the integers mod n, I'm not going to write the full, z and z anymore. I'm just going to write it as z sub n. So z sub n with the integers mod n is an example of a quotient group. In fact, it is the quotient of the integers and a left coset by a number n. This n, z, is a left coset, which is n plus any z, such that, well, z is inside the integers. So that's a left coset. And then we mod the left coset out, or I think that's how it's defined. Yeah, that's sort of the point of the notation, or why it was denoted like that. So that's part of it. So modular arithmetic, if you guys recall from our modding out F.E.M boys, is basically it works like a clock. After I get to 12, we just continue going, but then we say it's PM now instead of AM. So 2 PM is congruent, we could say, to 2 AM mod 12. So speaking in like layman's terms, 2 AM is, well, the same in a way to 2 PM mod, we say mod 12 A or PM. So we're saying that 2 AM is exactly the same as 2 PM under the stipulation that the arm continues moving after one revolution, or after surpassing 12, it continues moving, right? Let's see, modular arithmetic, this one. And if I have a set 1, 2, 3, 4, and then 1 is my multiplicative identity. Of course, I'm not claiming this is a group. I'm just trying to illustrate the idea of a quotient, or I'm not quotient, modular arithmetic. If I mod this out by 4, I mean, I'm left with the set 1, 2, 3. I'm gonna expand this 5, 6 until 6, and I'm gonna mod it by 4. So that just leaves us 1, 2, and 3. But we've essentially compressed the entire thing onto this smaller set, because what we're now saying is that 5 and 6 are just equivalent to 1 and 2 respectively, mod 4. So 5 is congruent to 1 mod 4, or parenthesis. And 6 is congruent to 2 mod 4. So that's modular arithmetic. So how's it relate to quotient groups? Also, I think we discussed about the first isomorphism theorem and using it to prove about some facts about circles. And the first isomorphism theorem is basically, it's a theorem of group theory that states that if I have a homomorphism phi that maps G onto some set H, right? G mod the kernel of phi is isomorphic to the image of phi. Okay, so a majority of today's lesson will hinge on this theorem. I'm not going to prove it in this lecture, but we're just going to sort of apply it. So actually you can think of this, the kernel of phi, of course, is every element in G that is taken to the identity of H. And the image of phi, of course, is H, or at least a subset of H. I mean, this string is a homomorphism, not really a mapping between two sets or a function. Because functions and homomorphisms are not the same. Well, a homomorphism is a type of function or is a type of mapping, but not all mappings or functions are homomorphisms. There are homeomorphisms, there are isomorphisms, there are diffeomorphisms. There are even just regular morphisms between categories. There are functors, which is a type of mapping between categories. So yeah, not to go too much of a tangent. So at the end of this lecture, I will also provide you guys with an algorithm or a procedure for taking any possible thing out of context, so long as it has a slash in between. So it all started with a trip to the mall and me seeing a sign that's indicating a parking or an exit ahead. And I thought to myself, how can I take this out of context and make it into math? Well, quotient group. You can think of P here as a group, and exit can be a normal subgroup. It can be a symbol, exit could be a symbol for a normal subgroup of P. So we can say that exit is a normal subgroup of P. And this is what we call a normal subgroup. And normal subgroup is basically a subgroup. It carries the same structure as P. It's the same as P, but it is invariant under conjugation. So it's invariant under conjugation. And what I also want to show in the end, or at the end of this lecture, is that is the surprising relation between left cosets and these things. So as I stated a while ago, the reason for the notation for Z, mod NZ, is due to the fact that it's sort of related to left cosets. Okay, so first things first, say that P exit, where was it? First say that, okay, exit is a normal subgroup of P. What we just have to do, well, the thing is, in order to even construct a quotient group, we need to first know that it must be, the thing we're quotienting by, must be a normal subgroup of this set here. So it must be that for any element inside here, any element in here, I'll call E, and another element here in P, EP and P to the minus 1 is inside big P. So that's what we mean by invariant under conjugation. So any element E inside exit up arrow, it's just an entire symbol, okay? This doesn't mean anything else. It's just a symbol. Just like how 1 is a symbol for a quantity, right? Or whatever object you think 1 is. E here is a symbol, any element inside exit, and small p is any element inside p. So doing this operation, so I have an e to the -1 applied on p, and then e. If it's an additive group, if p is an additive group and x is an additive subgroup, then we would be adding these things together. And when we do add them together, according to the Peano axioms, it would so seem that it would be p. So e plus p plus e to the -1, and the additive inverse of e is minus e. And so it's true because, oh wait, so this is plus minus e. And that just sort of distributes e plus p minus e, and the e crosses out. And indeed, p is a element of p, as we claimed in the beginning. So there's a small proof for you. Why, if e is an element of x, it's a normal subgroup. But we haven't specified yet what exactly are the elements of exit. In fact, in my paper about this, or in my compendium about this, or the section of my compendium that concerns this, I treated exit here as a singleton set. It's one singular set that such that exit up arrow is a symbol for a congruence class that contains itself and its additive inverse, which is minus exit up arrow, or if you want to think of it in terms of the abstract terms, exit up arrow to the -1. And that's what I'm going to be focusing here, because I don't want to complicate the lecture further. Let's keep it simple and say this is a singleton set. Exit up arrow is a singleton set. It is indeed normal by the definitions I will soon lay down. And yeah, so let's get to it. Let's get to the actual thing that we're going to do. Okay, so our goal is to show that P mod, I'm going to use brackets because this is a singleton set, exit up arrow is a quotient group. An additive quotient group. Okay, so claim 1, P is an additive group. So I have a binary operator which is plus, such that it satisfies the group axiom. So every element plus another element is inside the set. So the result of that addition is inside the set. It's closed. Second condition is that for any 3 elements, if I switch them around or add 2 of them first and add another one, and then do the vice versa, it wouldn't matter, of course. And every element has an additive inverse, so negative numbers basically. And if I add them together, I get the identity element. And lastly, there is an identity element, such that when I add that identity element to any element, the element stays the same. The element we added to stays the same. And exactly, this is what the integers are. And the integers, z, is an additive group. Its additive inverse is all the negative versions of the elements, and its identity element is 0. Okay. So, yeah. So the integers is an identity, yeah, and we're going to show that this is an additive group via some predefined operations. Because the thing is, I can't just say this is the integers, because I don't want it to degenerate into a case where it's trivially just the integers, and we're just making the integers mod n. Although it is similar to the integers, I don't want it to have ultimately the same exact structure and the same exact elements. So I just want to note here that P is distinct from the integers, okay? And it is in fact a finite group. It's not like the integers, which is an infinite but simple group. So P is like, I could say, a finite cyclic group. It could be a cyclic group. It could be isomorphic to a cyclic group at the moment, but we don't really have a notion for cyclicness at the moment without defining our modulo operator or modular arithmetic. So we just run with the thing that it is an additive finite group that is presented, or which is expressed. And there are these things called group presentations. And group presentations are a more compact way of expressing group. Rather than writing out the set, you know, whatever your elements are inside, and then the predefined operation, we just write it like this. And then the generators of the set. Whatever element you see that occurs the most there in your set, and then some operation. I know this is a bit abusive notation because this is an inner product. You know, if we think in terms of differential geometry or physics, but it's just notation sake. What we're going to be using is one we're in. So the set, this is set here, and then this is the defining relation of each generator of that set. And generator is basically all elements inside the underlying set of the group that makes up the group. Or if we want to think of it as like a free group, I suppose. So all possible. So it's like the sort of the elementary symbols that make up everything inside that free group. So if I want to decompose every single element in the free group or in that free group, what I get from those decompositions, or the most recurring ones, go into this part, or this side of the angle brackets. And then this here is the relation, the defining relation between each. Now, this is where it's important, because when we do try to define a cyclic group, this is where we want to define that the numbers wrap back. Okay? Such that if I apply it again and again, right, it just wraps back. So for example, a squared equals a. So apply a and a again, and I wrap back to a. So a, and then back to this a. And this is C2. So the set A, such that a squared equals a, is C2. This is the presentation of C2, if I'm not mistaken. Okay, so enough with examples. So P is an additive group expressed as the presentation. So I will just list down the most common elements of this, which is just a bunch of P's. So P, I'm just going to index it. I'm going to use an index because it's all going to be using subscripts P1, 2, 3, 4. And it's a very, very general thing. It's very arbitrary. You guys can pick how many elements are inside here. And that's what my focus is really, is the quotient group part. So this definition is arbitrary, and I will use an index set because the index set is dependent on you guys. So P sub I to the minus 1, PT, PE, I'll use PE for exit. So this is the element right before exit, minus 1, and then exit, the inverse, the additive inverse. I'm just, for compactness sake, I'm gonna use to the minus 1. But this does not mean it's the multiplicative inverse, like the reciprocal. No, that's not what I mean here. This is group theory after all. I know it's abstract algebra, but we're not in elementary math here. Okay, so exit, up arrow to the minus 1, our identity element, which I'll just call E. This is not Euler's number, mind you. Not Euler's number, it is just an element E, such that if we add it to any of these elements, it does nothing to those elements. And then same thing, P sub I, but positive here. P sub E and regular exit up arrow. And there is no defining relation for this just yet. And I know it's a bit counterintuitive or contradicting that, well, you can make it as much as we want. It looks like it's somewhat bijective to the integers, but there is a bound. There is a bound, unfortunately. I can expand the entire underlying set to look like this. Dot, dot, dot. Exit. If you guys think that it's not quite bijective to the integers, I can make more elements beyond exit up arrow. But to keep things finite, I did make exit up arrow into the bound inside my paper, or in the compendium, or the section of the compendium where I talked about this. It's a p sub I minus 1, p sub e to the minus 1. I know the ordering is a bit off. I'm just going to switch that up. E and then I. And I here is indexed, okay, so it's a sequence of elements. It's not just one element, okay? And then the identity element, pi, p sub e, and exit up arrow. And the reason why it's exit up arrow is because I think what it was trying to meant to say was parking or exit ahead. This one, but I don't think that matters. Okay, so if I don't want a defining relation just yet on my group, that it just, the operation that's defined on this just satisfies the group axiom, the bare minimum for it to be a group, I just write bar nothing, or the null set, or the symbol for the null set, to denote that there is no other defining feature. Now I know that this makes it sort of degenerate into a sort of an integer or a subset of the integers, but here's the thing that differentiates it from the integers. And that is, whenever I add exit up arrow and its inverse to any element, element or inverse, I'm gonna keep it clean and just focus on the positive elements now. If I have, okay, here's claim number 2, or distinction number 2, for any, I'll call it psi, any element. It could be an inverse, it can be a regular element. So long as it's inside P, exit up arrow plus that psi is just equal to psi. So the X up arrow is somewhat of an identity, but we also want to make a distinction that it is not an identity, all right? The only thing, what we want is that it's an elements absorb it, just like the identity element E, but it is not the same as E on the nose, okay? It's distinct from E, but it sort of acts like E. I'm sure that you guys think that that just sort of claims that it is exactly just E, because what else would have that distinct property if it's trying, what else would have that property if it isn't identity, right? But the thing is, I don't want it to collapse into again. I don't want my group to collapse into a trivial case that is bijective to a subset of the integers or the integers. So yeah, there. So exit up arrow plus psi gives us psi, and then the exit up arrow. Oh no, sorry. What else? P sub E. P sub E is less than exit up arrow. Now, I claim this because, of course, over here, PE. And it's the element right below exit up arrow. So if I want to say that this here is bijective to, if this set is bijective or has a bijection with, let's say, the first six integers, negative and positive, then I'm pretty sure they would, and of course this would be 1 through, I know it could be an arbitrary amount of numbers, but let's say that it is 1 through 4, right? And exit as our bound already. There are no elements beyond exit. Let's assume now, just for now. Then yeah, there is a bijection between those. Of course, it depends on the bijection that you define it with. But it so happens to be that in the bijection, it is important that we identify, topologically speaking, identify or set an equivalence relation between exit up arrow and 6. And P sub E to 5. And then the rest is 1 through 4. And then the element, identity element E is 0, of course. Because additive integers. saying that that's isomorphic to the additive integers, and that also includes maintaining the structure. So that means the same laws are happening, and it still holds as a group. Okay, so because whenever we do an isomorphism between two groups, they need to maintain structure. Most notably, the operation between each elements stay exactly the same, or at least act in the same manner. And that's sort of the reason why rotating an object is sort of the same as cycling a bunch of elements inside a set. So like permutation groups are isomorphic to rotation groups, like U, the general linear group. They're isomorphic to Cn, or at least parts of Cn, or parts of C infinity. Okay, so that's an important thing. And the reason why I said this is because because the integers is constructed from the natural numbers, it employs order as well. I know this is not explicitly defined in the construction of the naturals, but what I want to say is that every element inside the set, underlying set of P here, is comparable. So if I take two elements, say Pi and Pe, I can compare them both together. And the same thing, all of these, everything that I will talk about here in this first part of the lecture will apply to when we actually do this with pronouns. Okay? So there. So actually the general idea is that I have that thing on the other side, on the right side of the slash, on the backslash, and then that's just a unique element there, and then the one on the left of the backslash is the group, right? So you can think of it as a as I said, you can think of it as a subgroup, a normal subgroup, or you can just think of it as some elements inside it, or one element inside it, or a symbol for an equivalence class of those elements, or a bunch of elements that are related to each other under a congruence relation, which we will expand on here, in order to define cyclicness, quote unquote, without using the definition of a cyclic group. Okay, so yeah, so this does nothing if added to any elements, and so does E, P sub E. Okay, so here's where I want to make things distinct. I said in my paper, I'm going to link it down below, I said in my paper that PE acts the same way as exit up arrow. That if I add it to any element, it will do nothing to those elements. Now, here's the thing. I wasn't very clear on that, and I want to make it clear now in this video. In the same example a while ago, wherein this is bijective to a 6 element, or actually 13 element subset of the integers, which is -6 up to +6, including 0. Exit, here's the 6th element, this is the 5th element. So what we can do instead of say that they sort of they don't do anything, is we can instead think of them as another P sub I, and then we do the operation I will define soon, the third point. And the third point is exactly how do we add the elements here? What is our notion of addition here? If we think of these P sub i's, or these I, as the position of every element in the set, so this is like the -1th position, the 0th position, which is just E, the first position, the second position, the third, and so on and so forth. I did this in modeling out femboys, and we're gonna reuse it here. So for some P sub I and P sub j inside P sub I plus P sub j is equal to P sub I plus j. Likewise, if one of these is negative, it's just P sub I minus j, or P sub j minus I. Okay? And there. That's our notion of addition here. Okay? So if I have if I have an element in the ith position and I have another element in the jth position, their addition is just the same as the P sub I plus jth position, or the P sub I plus jth element, or the I plus jth element. Okay? So there. I don't need to define further what it means. It's almost all of this is stated in modular arithmetic. and modding out femboys. Okay, so let's actually do the claim. So after I've defined all of this, let's actually do the proof for this. Why it's a quotient group. And we're going to employ the first isomorphism here. And the goal of each of these proofs that I will lay out for you guys is to show that it is bijective to itself. So the hint, if you guys want to pause now and prove it yourselves, the hint, or I know, I would appreciate it if you guys found a better proof for this, but here's my way of proving it. So the hint is that any group G is isomorphic to itself. Okay? So it's an obvious fact. Any group is isomorphic to itself. Z is isomorphic to itself. N is isomorphic to itself, if N is so happens to be a group. R is isomorphic to itself. Each of these groups, whether additive or multiplicative, is isomorphic to itself. An isomorphism is somewhat like an equivalence class in the way wherein if I have two exact things that are isomorphic, I can switch them around. Now, it might be the case that it is not isomorphism, but an isomorphism is invertible by definition. It's a bijection between two elements. So therefore, I can switch the two sets, right? And so therefore, this fact holds. And this hint is what is. I'm not going to prove this hint, but there it is. So pause the video now, or this lecture now, if you want to prove it yourself on why it's a quotient group. Okay. So if you're back, or if you don't want to solve it yourself, okay, let's do it. So the goal is to show that P mod x up arrow is isomorphic to itself. And we're going to use the first isomorphism theorem, which I stated at the beginning of the theorem, of the video or the lecture. Okay. Okay. So I'm gonna let let F that maps G, oh no, not G, P onto Y be a homomorphism. So let there be a homomorphism between P and Y. P is our group here, and Y is another group which we define to be the set of all congruence classes, or all symbols denoting congruence classes that are under a specified congruence class, which we're going to identify by this map. Okay, let it be a homomorphism with the map. So each piece of I in P is mapped to some piece of I congruent to piece of J mod exit up arrow. So that is our congruence relation there. Okay, so it's the map. Okay. I'm gonna denote every single element that satisfies this relation with respect to one element P sub j as just bracket P sub j exit up arrow. So this is defined as P sub j. Oh, okay. P sub j bracket exit up arrow. So the set of all P sub I that satisfies this congruence relation, exit up arrow divides P sub I minus P sub j is part of this congruence class, which is a set of all of them. And that is discussed, I think, in foundations, or in modding out. So every single piece of I that satisfies this. So that implies, not really defines, every piece of I such that piece of I, exit up arrow divides piece of I minus piece of j. That's what we use for divides. We use a vertical line over there to say that x divides the difference between p sub I and p sub j, and that is precisely this. I'm defining it. Okay. Okay. So isomorphism with that map. The next thing to say is that first things first. Okay. Now we see y is the set of all of this. Alright? So y is defined to be the set of P of congruence classes with respect to exit up arrow of such that P sub j is an element of P. So that's y, which we say to be the image of F. So I'm gonna say let y define that, and the kernel of F is precisely exit up arrow, or the set of congruent classes of exit up arrow with respect to itself, which is just exit up arrow and negative exit up arrow. And that's just exit up arrow and then minus exit up arrow and any other possible elements beyond exit up arrow that is congruent to it under its own mod. Okay, that's the kernel of F. By the first isomorphism theorem, by the first isomorphism theorem, indeed we see that P mod the kernel of F is isomorphic to the image of F. I'm just going to use IM instead of image. And thus, indeed, we see when plugging all of this together, and it does make sense that that is indeed the image of F, because every piece of here, piece of I is, sent to these, sent to at least a subset, or sent to some parts or some elements of this entire set, right? This entire set, you don't see it. And the kernel is exit up arrow is practically an identity of its own set, right? And it is practically the identity of y as well, or rather, it is exit up arrow. It is sent to the identity of y on this congruence class, because this would be sort of equivalent to 0 as well. In a way, that depends on how you define P here. If it's finite enough and you mod it enough, we're in, yeah. And if you do cut it off at exit and there are no elements beyond exit, it is true that it is indeed the thing under this mod thing here, because exit up arrow, mod exit up arrow gives 0 or implies 0 in this case. Okay? And indeed, under this map, if I make P sub I here exit up arrow, and then what else would be congruent to it? Just exit up arrow. Okay? And that would be 0. So indeed, it is sent to 0. Or E in this case, sorry. Which is the identity of Y and P. So therefore, this is true. So it is indeed the kernel. Okay, okay, so continuing, and thus it does holds that P mod the singleton exit arrow, which I will just use as a symbol to denote this congruence class. this is just a symbol for this congruence class, is isomorphic to itself. Again, I would appreciate it if you guys were to find a better proof for this, but there it is. This is the proof. And this is the hint, that any group G is isomorphic to itself, and just use the first isomorphism theorem. Okay, so there it is. Now that we've discussed, signage and stuff like that, let's go move on to actual pronouns, the actual thing you guys came here for. And thank you if you're still with me at this point. This is a very important thing here, and we're gonna reuse this proof a lot when we start playing around with pronouns. So, that was one theorem. Here's theorem number 2. You guys see it? Yeah, you guys can see it. More space. Theorem 2. They mod them is a quotient group. Oh, I'm sorry, I forgot to show you guys why exactly the previous one is still a quotient group. I forgot to state why. Okay, so the other thing a while ago, P mod, exit up arrow, is still a quotient, is still a group, because for every congruence class, right? For every congruence relation, A mod B, A congruent to B mod exit up arrow. Okay, I have a B congruent to A mod exit up arrow, such that if I plug this into here, it gives me B mod B exit up arrow, and then that just gives me 0, or E, the identity element. And so that's our inverse for this operation. That's really all I need to tell you. You guys can figure out the rest. All I need to say is that every congruence relation here has an inverse congruence relation that sends the element that we first put into the congruence relation, or map to the congruence relation, to the identity element. And that satisfies the most important group axiom. Okay, and there is an identity element that's just E here. Okay, or in this case we're making it congruent to E. Okay, there. Okay, let's get back. Let's get back to they them. So theorem 2. Theorem. They them is a quotient group. They them is a quotient group. We're gonna do the exact same thing as we did with P mod exit up arrow, and say that them here is a singleton set. So this implies this is equivalent to they mod the singleton them, where them is a symbol for the congruence class of them under itself, which is minus them, or if it's an additive group. If it's a multiplicative group, I think it will require us to try to make a bijection with the rationals, but I want to simplify this lecture, so let's just stick with the integers for today. Some other teacher perhaps, or if you guys want to apply as a professor, you guys can expand upon that if I haven't done it yet. Okay, so proof. We're going to use the exact same facts. So, as a while ago, they them is essentially the same as P mod exit up arrow. We just renamed some things. We just renamed or switched out the elements, but it carries the same exact structure as P and stuff. Them, they here is now group. Them is a normal subgroup or an element which we mod by. Okay. All right. And same thing happens. We also employ structure and order. There's also order here, and you guys already know the gist of it. Just rewind. Okay. So let F maps they to y be a homomorphism. I'm just going to shorten to homo because homosexual, haha, funny. With the image each t, I'll call it t now because it's puro. There's a lot of t here. Okay, t sub I is taken to t sub I congruent to t sub j mod them. Again, them is just a symbol. It's just a symbol. But in the end of the lecture, I will also show you guys that well, we have some connection with a previous FEM exposition on math lecture about proving that A comes before B mathematically. And this is actually, I'll just say it now, this, them, and also the exit up arrow, excluding the arrow because the arrow is not part of my alphabet that I constructed. All of those are elements of the free group over E and then the comparing operator. Okay? They're elements of the free group over that set, or that ordered set. Yeah, or structure. So there. Alright. So T sub I is mapped of T sub I congruent to T sub j mod them. And Y, of course, is defined to be the set of all of those. So all T sub j under them. So T sub j, this is inside they. Alright, and then let the kernel of F be equal to, of course the kernel of F is just congruence class, as I stated a while ago, of them with respect to module by itself. And then image of F is equal to, of course, Y. By the first isomorphism theorem, they mod the kernel of F is equal to, or not equal to, isomorphic to the image of F, and thus they mod the singleton them is isomorphic to itself. They mod. Yeah, doesn't follow. Yeah. I can do the same thing with he, him, she, her. Hell, him, they. Instead, I just have to replace they with him. Okay. So if I want he, they, I'm just gonna replace they all throughout this with him or he. Maybe I'll just erase the T into Y so I don't waste ink. There. If it's he, them, same thing. Just replace they with he. In fact, this is sort of the algorithm I'll tell you guys. Excuse me. Okay. Sorry, I had to fix something. Okay, so this is actually the algorithm that I want to tell you guys here at the end of this video, or near the end of this video or this lecture, is that in order to do this, we just pick a set with an arbitrary, amount of symbols, whichever symbols you want them to be. They can be part of, the alphabet, ordered alphabet, a Latin alphabet that I defined in an F.E.M episode. And then what we just do is just, find an element we want to mod out by, and then we just construct this congruence relation. And then once we construct a congruence relation, we create a homomorphism between, our original group and the group that we're itself mod, basically, that element. Which is a set of all congruence classes we can possibly construct under that congruence relation. And then we just use the first isomorphism theorem to show that resulting structure of modding out, our original group by that by that subgroup or that element is isomorphic to itself. And there. And what's the takeaway for this video? The takeaway is there's a lot of drama nowadays when it comes to pronouns. Wherein, oh, you misgendered me, you should be cancelled on Twitter. My point in this video is that they're just symbols. They're just labels. And I don't think that we should concern ourselves with what we label ourselves with. Okay? If there's anything you can take here in this video that's not math oriented, it's that these pronouns, they're just symbols. They're just labels for whatever we want other people to perceive us as. I use he, him, but ultimately, I don't care what pronouns you guys use, so long as it's convenient for me to call you guys, right? Alright? I know that may sound a bit selfish because I'm only concerned about my convenience and not your feelings, but the point is, these are just labels, and we shouldn't care if other people don't label us properly. We shouldn't care, frankly. I don't care. If I'm a femboy and somebody calls me a her, why not? But I'm a cisgender. So, in the end, you shouldn't care about labels. These things are just labels. They're just symbols for what we are. And we shouldn't let them dictate whatever our lives are. So, there. So a funny little discussion with a nice moral lesson. I'm not good with moral lessons or social stuff, so here's the video, or here's the lecture. So yeah, this is a clickbait worthy title, and this is a good place to stop.